Hello, welcome everyone to the workshop on Next Communication Technology. And I'm happy to start our first session with a talk by Professor Chockalingam. Professor Chockalingam is a professor in the Department of IISc. He obtained his PhD from IISc in 1993. He was a postdoctoral fellow and a project scientist in the Department of UC San Diego from 93 to 96. He was with Qualcomm San Diego as a staff engineer and manager from 96 to 98. Since 98, he has been a faculty at IISc Bangalore. He has served as the associate editor of IEEE Transactional Wireless Communication, IEEE Transaction of Vehicular Technology, IEEE JSAC, and IEEE JSTSP. He is a recipient of Swarn Jayanti Fellowship and the J.C. Bose National Fellowship from DST Government of India. He is author of the books Large MIMO Systems and OTFS Modulation Theory and Application by Cambridge University and by IEEE Press. So with this, I would like to invite Professor Chockalingam for the talk.
Okay, so very good morning to all of you. It's a real pleasure to be in IIT Kanpur again. So first of all, let me thank all the organizers of this workshop for having invited me and giving me an opportunity to talk to you all regarding a topic of current interest, not current interest, I would say, next decade topic of interest. So, and on this occasion, I think wish Professor Chaturvedi a happy birthday as well as congratulations on his new position, right? So with that, I'll start. I have 40 minutes to talk, which means 35 minutes of talk and then 5 minutes of question answers is what I was told. So we have started ahead of time, thanks to organizers. So maybe if I eat away some 2-3 minutes, bear with me. The topic which I'm going to talk about is going to be learning, which is AIML, is what we immediately think about it. So that is correct. So that is represented by this kind of a network. And I also have this other thing, which is ZAC OTFS. ZAC OTFS is a waveform. ZAC stands for person's name. ZAC transform by the name of the inventor, Joshua Zack, in 1967. And OTFS stands for orthogonal time frequency space. It is a waveform, just like OFDM is a waveform, OTFS is a waveform, a Zack transform based OTFS modulation waveform. In addition to that, it also is a radar sensing waveform. So we are going to talk about that. And the work is done jointly with my MTech students who just graduated. Chetan finished his MTech with me and he just joined Qualcomm 1 month back. And Arpan Das also did MTech project with me. Last week, he went to UT Austin to do PhD with his Jeff Andrews there. So this is the brief outline. I'll talk about what ZAC OTFS, which is a new waveform. Now the question becomes repeatedly, why you need a new waveform? So why a new waveform? I will give some motivation for why a new waveform is required. I think many of us know, but I'll just highlight from there. I'll start. I'll go through what is ZAC transform, inverse ZAC transform, how it is equivalent to, you have the DFT and IDFT in OFD, okay? And I will talk about the transmitter receiver block diagram. And in that, one particular task, and that is a crucial task, is estimation of the channel, which is a common issue in all the communication transceivers. If you use ZAC OTFS waveform as the waveform for your communication, how to do channel estimation. So you have classical techniques, you have non-classical techniques, including learning. So what we will talk about is set the problem and then see what learning can do, and then much different than what we do without learning. So that is that, and one small summary. So this is supposed to be presented in Istanbul in the coming weeks. So I'm just making a dry run for the student. If I use these slides, he can use some of these slides for his presentation in Istanbul next week or a few weeks from now. Okay, so this is a standard slide. So which I think even the head talked about. Wireless is asking for or demanding all the times higher data rates, higher spectral efficiency in terms of bits per second per hertz, in terms of energy efficiency. These are all old demands. 2G to 5G, these are all old demands. But some new or current focus is on slightly different, going from 5G to 6G, is mobility. You want to have higher mobility, which means the speed at which the users can move can be more. And number of use cases can be different, varied. And then more importantly, you also need radar sensing support. which the intelligent transportation system, autonomous driving, brings in sensing the environment around you. So can we do communication and sensing together? So that is an additional requirement. So these are the general things. And if I have to look at the evolution, 2G and 3G, if I have to say how did it fare, it did well in the voice communication regime. It asked for only voice communication, right? Up to 3G, and little bit of data support was there. But then 3 to 4G was a big jump, and that is data rich, and internet happened, and it is internet driven. So I would say 4G and 5G is internet driven. Suppose if you say 5G to 6G, what will drive? Obviously, many people will agree that it could be AI driven. AI driven not only in the applications domain, but even the implementations. Companies will be looking for taking advantage of learning as much as possible, even in your design inside the chips and smartphones, also in the applications. So that is how it goes. And then in 6G as we go, new technologies are emerging. And one such new technology is new waveforms. Okay, new waveform is one among many new technologies that will come. Okay, that is the focus that we will touch upon. Okay, so I say a new waveform. So first, okay, so this, okay, good. So what is ZAC OTFS? Before I go, why new waveform? What is the ZAC OTFS? ZAC OTFS is a waveform for two purposes simultaneously, if you can exploit it, if we can exploit it, for communication as well as radar sensing. Okay, and in what domain this waveform is? This waveform is in the delay Doppler domain as opposed to time or frequency domain in the past that we have been doing. So that is the crux. So we will be highlighting only the modulation waveform aspect in this talk for half an hour, but radar sensing for a later time. If Kanpur invites me for a later talk, maybe I'll be talking about radar sensing at that point in time. So this is an interesting analogy, I thought, for people to appreciate what is the current and what could be future. You said next decade, right? An analogy or juxtaposition of current legacy waveform to ZAC OTFS. You can say linear time invariant systems we teach in our courses at the BTech level, LTI systems. In LTI systems, if you want to do communications, the waveform of interest, which is very popular and very efficient, is OFDM, cyclic prefixed OFDM. So OFDM came from wireline channels, not wireless channels to start with. Although 5G works with OFDM, it came from wireline, which is time invariant and linear. So we took time invariant waveform and then applied it into a time varying channel, but slowly time varying up to some point. So that is CP OFDM. Now, what OFDM is to LTI channel, recognize ZAC OTFS is to LTV channels, linear time varying channels. Okay, that is one. Now, where the information resides in OFDM, it resides in the frequency domain. You do IDFT to convert to time. Now, analogy is, where does information reside in OTFS? It resides in delay Doppler domain, and you need a transform to convert it to time for transmission. Now, what is a theory that is required for you to understand and describe this technique is Fourier theory, right? Which we studied long back. But what is the theory for describing and understanding ZAC OTFS is ZAC theory, which we don't teach, which we should teach, right? And the transform of interest is Fourier transform, which we know very well. And the transform for doing the transformation from delay Doppler to time and back is ZAC transform. That is the mapping. And importantly, Fourier transform was invented by Fourier in 1822. And it is used for modulation in 1966. One of the applications of Fourier transform is modulation. And that happened in 150 years later after it was invented. Now look at this here. Joshua Zack wrote this paper in 1967. So their representation theory, basically it originates from representation theory. You have a time domain signal, I can represent it in different ways. And one of the representation he talked about was KQ representation. He's a mathematician. And that paper got appeared in 1967. That KQ representation, take it for communication purposes, delay Doppler domains. KQ representations, delay Doppler representation for us engineers, right? Now, that happened in 1967. In 2022, we wrote the papers with Ronnie Hadani, Saif in IIT Delhi and Robert Calderbank in Duke. So we wrote the paper in ZAC OTFS in 2020. So it's about 40 years. So you can see 150 years for Fourier to come into the modulation and ZAC to come into modulation. It's 150 years versus 40. So that is something which is interesting. And also we know that the mathematical operation that describes the entire transceiver chain in OFDM is linear convolution. Although we don't probably teach that with linear convolution in place, we just say IDFT, DFT, and then engineering view. But if you go through the operations, it will be linear convolution. So it will be twisted convolution in this case. I'll talk about it later. So now, why a new waveform? Okay, historically, physical layer waveform has been the differentiator from one generation to another generation. Point number one. So which means 1G we had FDMA, TDMA with GMSK modulation, CDMA again 2G itself, and then as we progressed, the earlier waveforms disappeared. But from OFDM, we have to move, or do we have to move, right? CDMA to OFDM happened in 4G and it continued in 5G. Will it continue in 6G, or should we look for alternatives? There's a question mark. Okay, what are the reasons? I said high mobility support, high speed trains. Ahmedabad will see bullet trains soon, and we will see more of that, because once Vande Bharat happened, many Vande Bharats are flying across very major cities. Same thing, bullet trains will happen in India, and aeroplanes do not have coverage now, but they will be having. They are hundreds of kilometers per hour, 500 kilometers per hour, 300 kilometers per hour, 1000 kilometers per hour. What that means is, translated into Doppler shifts, they'll be in the order of kilohertz. Right now, your 4G, you are driving at 100 kilometers per hour at 4 or 5 gigahertz carrier frequency. It is going to be hundreds of hertz, which is in the LTI regime, linear time invariant regime. You go to higher frequencies and you go to high speeds, your Doppler will be much higher, and you will go to LTV regime, where the waveform is going to be, can be different. So non-terrestrial networks, drones is a new technology. If I ask anybody what is a new hot topics, obviously drones is one of them, robotics is another, AI is another, ML is another, and then quantum is another. So these are the things around which we are now focusing, and then drones are going to be playing a big role. NTN, non-terrestrial networks, LEO satellites, of course we have the internet on the sky, they are going to be new, and radar sensing, as I talked about, is going to be. So in all this, legacy waveforms may or may not support these new requirements, and because of which there is a need, or there may be a need for new waveforms. Okay. So that being said, that I have to do one slide on transform, which is of interest, because this is the one on which the Isaac OTFS resides. Okay. Isaac transform, first of all, it has to be, there's a parameter for the Isaac transform, and that parameter, what we call that is a delay period, which is tau p. Strictly speaking, there are two parameters, but they are interconnected. Tau p is the delay period, nu p is the Doppler period, and tau p nu p equal to 1. So if I know one, the other one is fixed. So it is a part of definition of Isaac transform. What does it do? It maps a time domain signal into a DD domain signal, which is a delay Doppler domain signal, but more importantly, quote unquote, quasi-periodic DD domain signal. So I'll come to what is quasi-periodicity repeatedly. Quasi-periodicity, twisted convolution, these are all new things that will come here, and I'm trying to put it in the beginning itself. So this is the expression. This is the expression for Isaac transform. Given a time signal, take the Isaac transform, you have this expression. Inside this expression, which is a summation over k belonging to all integers, right? K tau p is there. Okay. So this is the basic transform. Just like you have Fourier transform, this is the Isaac transform. This side you have a regular parenthesis, which is having a time continuous domain representation, which is delay and Doppler. Tau is delay and nu is Doppler. And you have the Isaac transform, and this is the corresponding to AFT, which is a continuous time signal. Now, this definition has this quasi-periodicity property. What that means is, take AFT and then A tau nu, ask this, what is this shifted version? A tau plus n tau p, nu plus m nu p, that could be A tau nu multiplied by this exponential term. If this were to be equal to A tau nu, that is periodic in delay and Doppler, but it is multiplied by this term, so because of that it is quasi-periodic. In other words, along the delay, if I plot this in delay and Doppler, along this Doppler it is periodic. If I put n equal to 0, tau, and this is going to be nu plus m nu p, it is going to be 1, and this is going to be periodic. But on the other axis, there is a tilt I am showing here. All tilts are same along this axis, but from here to here there is a tilt, and that is represented here. So it is quasi-periodic by definition. Take a time domain signal and then take the Isaac transform, it is quasi-periodic. This is a representative of a single signal, which is a pulse, but it is going to have one fundamental pulse, but these are all infinite of them around, they are all replicas. We call quasi-periodic replicas. So this is the signal representation. Okay. So now this, if I call this as the delay Doppler pulse, this will be the basic carrier for information carrying. In OFDM, you have a subcarrier, which you show as a sync pulse, right? And on that sync pulse in the frequency domain, you put a OFDM, the QAM symbol or BPSK symbol. Now here, imagine a two-dimensional pulse, which is this in delay and Doppler. And it is not going to be a single pulse because of the quasi-periodicity. There are infinite replicas around it, but in the basic fundamental period, there is one pulse. On that pulse, I'll put a QAM symbol, and that is a modulation. And if I take that pulse and take the time domain, it is going to be, it is not a sync function, it is an impulse train over a finite time, and it is going to be modulated by a sinusoid. So this is the waveform. Okay. Now, I'm interested in saying inverse Zach transform because I have to do the other way. So what inverse Zach transform does is gives the time domain realization of a quasi-periodic DD domain input signal. So why I stress this quasi-periodic DD domain input signal is existence of a time domain signal is there only for quasi-periodic delay Doppler signal. If I have an arbitrary A tau nu, which is not quasi-periodic, which is general function, take inverse Zach transform, it will not exist. Only when the delay Doppler function is quasi-periodic, a time domain signal exists. And I have to convert delay Doppler embedded information into time domain. So in other words, I have to somehow have symbols which are discrete, which are QAM symbols, into continuous time. In between, inverse Zach transform is going to be there. But inverse Zach transform exists only when the input signal is quasi-periodic. So one thing which newly will come in Zach OTF is you have to periodize this information signal before you pass it through the transform to convert from delay Doppler to time. Okay. So this is the transform. This is the transform. If I have A tau nu, take the tau variable as t and integrate over nu and the limit 0 to nu p, and then do this, you will get AT. So inverse Zach transform is needed. Just like frequency domain, you have information symbols, you do IDFT, you have time. Now I have delay Doppler domain information symbols, I will do information inverse Fourier transform, and then I'll get time. And I'll do the opposite at the receiver. Okay. And another thing which is important is this twisted convolution will come again and again. What we have is two delay Doppler functions. It has this form for the convolution. So notation is convolution, but sigma is representing the twist. So this is a twisted convolution. If I look at these two functions, if I do this and these two, you will see it's a standard two-dimensional convolution. But this term in the definition will make that twist. Okay. So this is convolution, but this will give the twist term compared to a normal two-dimensional linear convolution. So this is a twisted convolution. The property is linear convolution will associate as well as commute. But this twisted convolution, because of this, will associate, but it will not commute. Okay. But this associative property will be helpful in writing the end-to-end relation in the transceiver. Okay. More importantly, twisted convolution operation preserves quasi-periodicity. What that means is, if I have A tau nu and B tau nu two functions, if any one of them is quasi-periodic, this operation between this other one may or may not be quasi-periodic, but the twisted convolution operation will give a C tau nu at the output, which is also quasi-periodic. This is a property which you can prove by these two slides. Apply this, and then this you will show twisted convolution, which I do in my class in my courses these days, right? So these three things are essential, whether you get anything more beyond this talk, but these are all things which you have to recognize as what we are not told in classes before, or even when you read, you don't recognize this highlights importantly. So that is what I made it in the first few slides. Now I say, okay, where do you put information? Okay, where do you, so now you are familiar with this, and this is the delay Doppler, what we call that as period lattice. So there is a tau p, which is the delay period, and there is a nu p, which is the Doppler period. And I have this box, which is the fundamental box, which is 0 to tau p, 0 to nu p, and this box is a fundamental box. That is my playing field. In that play field, I mount multiple symbols and call that as the frame. Just like you have m subcarriers in a OFDM, and you put m symbols there, and then that you call that as one OFDM symbol or a frame. right? Now, same thing, instead of M subcarriers, look for this fundamental box with 0 to tau p, 0 to nu p. Again, inside that, I mount multiple symbols. Okay, what I do here is take this fundamental box. These are all replicas. Okay, these are all replicas. They will be there. You have to deal with them, but they are necessary. If you call them as evil, they are necessary evil. But they are enablers, because without those replicas, you will not get the existence of the time domain signal, which is needed for transmission. Okay, this red box is what we call this fundamental period, and this is the fundamental period. This is the fundamental period. So in that, I mount, suppose if I take this tau p divided by m, where m is the number of delay bins. So on this axis, you slice them, m delay bins. On this axis, slice them, n Doppler bins. So mn delay Doppler bins. You can see this. This is mn delay Doppler bins here. Now this is one delay Doppler pulse, which is like here. For this, these are all quasi-periodic replicas. Likewise, for each one of these points in the fundamental period, mn of them, quasi-period things all over. You have to imagine, because once you understand that, you can do signal processing very well. Because without this grasp, what you want to apply as standard signal processing techniques that you learned in your signals and systems may not be adequate. They will be useful once you cross this basic understanding that information symbols are ported here. Now, when I take tau p divided by m, I call this delay resolution. This delay resolution is partly in OFDM also. What we do is, suppose given a bandwidth b, what we do is number of subcarriers, then I have subcarrier spacing to be that whole bandwidth divided by number of subcarriers. Something similar happens here. If I give you b certain bandwidth, that is your resource, and certain time interval over which you can signal. So that is b is given, time of signaling is given as t. This resolution on the delay is 1 over b. So in other words, that delay is going to be spread based on the amount of bandwidth that you are giving. So more the bandwidth, narrower will be the resolution. Lesser the bandwidth, wider will be the resolution. So that is 1 over b. Likewise, this resolution on the Doppler will be 1 over t. More is the time given versus less is the time given. You will have delta nu, which is the resolution on the Doppler, which is extra. This was, you can relate it to OFDM in some way, but this is extra. Suppose if I give this as my, so where do I start? I start with designing tau p nu p. Like in your OFDM, I have to be given certain bandwidth. I have given you a certain bandwidth, which is 10 megahertz, and I have 1 millisecond as resource. And I have to pick, let's say tau p, I picked as 50 microseconds, nu p, which is 20 kilohertz, because they multiply to unity. If one is given, the other one is fixed. Okay. So these numbers are fixed. I'll come to that, how to choose tau p nu p later. Okay. Suppose as an example, 50 microseconds and 20 kilohertz I have chosen. Then what I have to come up with, how many symbols I can mount in that resource. Okay. Now this delta tau is going to be 1 over b. So which means m is tau p by delta tau, which is 50 microseconds. This delta tau will be 0.1 microsecond, because this 10 megahertz is inverse. So that is 0.1 microsecond. So m equal to 500. So b will give you the delay resolution, and the delay resolution along with tau p will give m the number of bins on the delay. And likewise, t is going to give you 1 over t for delta nu, which is 1 kilohertz, and nu p is 20 kilohertz. So this is divided by this is 20. So in other words, t will give you the Doppler resolution, and the number of subcarrier, number of bins on that is going to be decided by nu p divided by this. So in other words, 520 is what you choose as the number of symbols that you can put in the tau p nu p box. In certain bandwidth of a m subcarrier system, you will have m subcarrier, m symbols. Here you have a box, which is fundamental period, which has replicas all over the place, but signaling is in the basic information grid. And there you put mn symbols using this numerology. Okay. Now come to the transceiver. So I have said how to multiplex. Now this will tell me very easily what is happening. It looks very clumsy. It is not clumsy. Now that I have the channel, okay, this is the channel which is doubly spread, time selective as well as frequency selective, but I represent that in delay Doppler domain, one representation, keep it. and this is the additive white Gaussian noise. This is the channel. Above is transmitter, below is receiver. This is a time waveform. I should get a time waveform which is S of t, S time domain t. So the first thing that I have to do is inverse Zach transform. Okay. So I have a requirement for this signal, which is a delayed Doppler signal, to be converted into time. This should be quasi-periodic. This signal which is coming to the inverse Zach transform should be quasi-periodic. And there are two things which are done to the left. I have to convert this input to the inverse Zach transform to be quasi-periodic. Number two, I have to limit it in finite bandwidth and time. Okay. The quasi-periodization is happening in this. It may not because of lack of time. Assume that these operations are essentially going to give you, these are the information symbols XKL. XKL are the QAM symbol where K goes from 0 to M minus 1, M QAM symbols. L goes from 0 to N minus 1, together is Mn symbols. So this is what I want to transmit. I create a quasi-periodic signal in the discrete domain and lift it using this operation, make it continuous, and this XDD tau nu is this quasi-periodized continuous time delay Doppler signal. This is just raw information symbol which are discrete. First I quasi-periodize in the discrete domain, then lift, and that becomes continuous delay Doppler domain in delay Doppler, right? So that I do pass it through a filtering operation. That filtering operation is supposed to contain the signal within B and T. So that is going to be a filter. If I use this as a filter which is not there, it is an infinite bandwidth, infinite time kind of a signal, because these are all impulses at deltas. Okay. So you contain it into finite B and T, and that is the purpose of this pulse shaping filter. But this is a two-dimensional filter. It is a continuous domain filter, and it's a delay Doppler domain filter. We have been talking about filters in frequency domain, but this is delay Doppler two-dimensional. And that is going to be, operation-wise, is going to be twisted convolution operation. That filtering that we talk about, if there is a filter, that filter is a twisted convolution operation. So what that means is, this is a non-quasi-periodic signal, and this is a quasi-periodic signal. Output is quasi-periodic because of twisted convolution. Okay. So once that is there, then this exists, and then you pass it through the channel, and you receive the time domain signal, do the thing, because Zach transform definition now comes into play. For any time domain signal, you get a quasi-periodic output which is in delay Doppler, continuous. Then that you match it with the transmit pulse shaping filter with use the filter, which is a twisted convolution filtering. Then output is what we want to process, and that you discretize by using sampling at the points which are this information lattice points. At these points you sample when we say sampling. So you have the discrete, and this you can process. Okay. So you see the picture where this is the input and this is the output. Okay. And in between you have three things which are happening. One is a transmit pulse shaping, twisted convolution operation with respect to this XDD tau nu. This resulting signal, it comes to the channel, which is physical channel represented in tau nu. It is time channel, but represented here. And then there is one more twisted convolution operation. This YDD or WRX tau nu at this point, which you are sampling, can be written in this form. So this is the neat thing about the theory, which we say Zach theory, which is very systematic, formal, and elegant. Just like Fourier theory is systematic, formal, and elegant for OFDM. Right now, you can say that Zach OTFS, you can write it in a very compact form. All the things that happen here, there is much of math inside. A lot of double integrals will be there. If you see that this is a double integral, this will be a double integral, this will be a double integral. But all these things can be neatly written as, this is the input, this is the output. The whole thing is a cascade, which we have been teaching in LTI system. If you have a linear time invariant system, H1 of t, H2 of t, Hn of t cascade, you simply connect them using linear convolution. Right? We prove that in the class also. Same thing can be proven. This is one box, which is WTX. This is another, which is channel, physical, and WRX. So this we call that as the effective channel. My problem that we want to address is estimate this channel. Right? The problem is you have to recover from YDD KL this XKLs. For that, I need to know all the things that are there here, which is called as H effective tau nu, which I want to estimate. So I have described the transceiver operation in terms of twisted convolution and what each does, and set up a question how to estimate this, because observing this after quantization, after sampling, how to get this XKL estimates using the knowledge of H effective. Initially, you can assume it is perfectly known and you do device algorithms for detection, but I have to estimate. This is where learning we want to exploit. Okay. The way I have to say is this equation after a little bit of manipulation can be written in this form. This is the discretized version or the sampled version that can be written in this form. So this too is the first paper which is published in November 2022, bits information theory. And this relation y, which is equal to this collection of mn received signal samples in this vector form. X is what you transmitted as mn information symbols in this form, noise, and this H effective is this expression. And in this expression, this H effective is there. This H effective is this twisted convolution of all these things. Effective channel is not the physical channel. It is the filter, physical channel, and the filter. That effective channel I have to estimate. So that is here. So for me to estimate this H effective, I have to estimate this taps. What we call that as in OFDM also we say channel taps. Here also there are channel taps in the delay Doppler domain, MN taps, because there is MN, and that is to be, if I estimate this, I can calculate this. If I calculate, I have this equation, and you can apply all the detection algorithms and decoding algorithms. Okay. So the problem is H effective is the problem that I want to estimate. Now, one point I would say is WTX and WRX, right? Particularly WTX plays a big role, because when I say that it's quasi-periodic LISs, that LISs may come into the fundamental period if the filters are not well localized in the delay Doppler domain, right? I say that this waveforms, these are the filters. For example, this is a sinc filter. You can see this is the delay and this is the magnitude. You can have along the other dimension also a same thing, because this is going to be a product of a sinc in delay and a product of a sinc in nu. Together it is the transmit filter. This filter has this in one dimension, which is delay. And mind you, it is the best filter from an interference point of view, because it will have nulls at the information grid points. Each one of these points where null occurs in sync is that information grid points that I showed. So in other words, if everything is synchronized, if there is no other issue, there is going to be perfect signal there, because there is no interference from LISs to this. So because of that, that is good. But the problem is side lobes. Big side lobes can enter into deep inside to the next box and create aliasing interference. So which is not there in OFDM, which is there here, because in OFDM, you have the interference as long as your Doppler shift is less than the delta F that you're talking about as the subcarrier spacing. If it is small, you can, we can go ahead, loss is less. But here, something equivalent, the LISs should not come into the fundamental, because fundamental is where I want to process. But filter, if it is not localized, it may come in. But a sinc filter is a good filter, because at the sampling instant is zero interference. But then it has side lobes, so it has consequences. The point is, in estimating H effective, the signal shape is going to contribute to some extent the performance. Okay. Now, how to choose this tau p nu p is one slide. When I say tau p nu p box, I have to choose. Earlier I said 50 microseconds and inverse of that as the nu p. How to choose that? That is supposed to be from the spread of the effective channel. When I say spread of the effective channel, delay Doppler spread of the physical channel. Doppler spread is going to be depending upon the mobility, carrier frequency. Delay spread is going to be the size of the cell, reflectors around you, and that is only the physical channel. On top of that, the effective channel have the delay spread of the filter at the transmitter and filter at the receiver. The whole thing, if I call this as tau max, as the maximum delay spread of the effective channel, that should be smaller compared to tau p. In other words, this is system information. The physical channel spread and the filter spread is a information which I know as a system engineer before, and then fix a tau p which is more than that, 1. And same thing is true for nu p. Doppler spread is known and the Doppler spread of the filters are known, and that, if I call this nu max, that should be less than nu p. So these two, if you do, then the fundamental response will remain in fundamental response. Quasi-periodic guys will remain there, which we call that as crystallization condition, right? Many things happen in a good way if tau max is less than tau p and nu max is less than nu p. So you have your choice to make in tau p, nu p, and that is related to B and T earlier as I showed. But if this is not met, this response, suppose this is Doppler is more, so it is getting into the other boxes. So in other words, I want to do processing in the fundamental box here, but this alias is going to come and interfere. So we call that as aliasing interference. So we want to operate this. So tau p, nu p choice is yours, and that is decided by the system in terms of delay spread and Doppler spread. Okay. Now I want to do the remaining 5 to 10 minutes on the channel estimation. So what do? You send a pilot, in this case a single point pilot. This is the data, and remaining are all empty, and I want to estimate the channel using this. Subsequently, I can send a data frame which is full of data, so I can estimate during one pilot and do the detection using the estimated channel in the next frame. Okay, what are the two approaches? Again, conceptually, what we normally do in the classical way of channel estimation is send a pilot, determine the model that we gave to the channel response. We give a name to the channel response, name or model. When we say a certain number of taps, each tap is going to have a certain delay, it is going to have a power delay profile, and there's going to be a Doppler. So this is a model that we fit in. We call that as model dependent kind of channel estimation, where if there is P paths, each path has a delay, a Doppler, and a gain associated with that. You estimate those model parameters, right? And that is the first thing that conventionally we do. We are taught to do. We do that even today, whether it is one system or the other system. We do estimate the physical channel, okay? And that physical channel, we model it and then estimate the model parameter. We don't estimate the channel. We fit a model, you estimate the model parameters and pretend that the model parameters are good enough, okay? So that is fundamentally what we do, and I can do that even here, okay? I do estimate this tau I, nu I, hi, which are the individual paths, gain, delay, and Doppler. Hats are the estimates using classical approach, okay? But I have to get that H effective matrix. So in between, I have to do many things. From this, I have to do the physical channel response estimate. I have to convert that into H effective, which is including that WTX, WRX, there is another stage, and then discretize. After getting this, you sample it and then plug it into that equation that I talked about as matrix in terms of summation of small H effectives, taps. So all these things one can do. It is consuming time, complexity, but it is conventional. Two things are very clear. OTFS you don't have to do. ZAC OTFS you don't have to do. Number one. Number two, you can exploit learning techniques smoothly, both, which is not there. Here also people have done a lot of research. It is there in your chips in various waveforms. You can do that, but we say that it is not needed. Particularly when the physical channel tau I, nu i's, they are fractional. When I say fractional, not multiples of that grid, resolution. It could be arbitrary value. If the fractional values are there, estimating the fractional components of the delay Doppler is going to be messy, more involved. Of course, a lot of techniques are there. But here, model-free approach is all you have to do is transmit this and simply read off the received signal in some support set. That's all. It is a nature and beauty of this twisted convolution, and no matter what the fractional values are or integer values are, simply it allows you to read off. Imagine you estimate this, do this, do this, do this, and then come here. But to come here, all I have to do is just a read off operation, which we call as model-free. So this is a major advantage of ZAC OTFS, but it has some limitation. In the sense, when I read off in the fundamental region, right? That YDD, whatever I called as YDD as the receiver after sampling, I read it only in the fundamental box. But that fundamental box has aliases. That aliases are interference, and in addition, noise is there. So now these two guys may harm or compromise your estimation accuracy. Now that accuracy I can improve using learning. So that is the main story, okay? This is the channel, if I have the pilot exclusive. So you see this box, this is what I am going to do in the next few minutes. Okay, I have exclusive pilot as well as superimposed pilot using spreading. I'll avoid, in the interest of time, superimposed pilot, but this I will spend 2 to 3 minutes and then say, see here, this we have all seen, right? This transceiver is the block diagram I showed here. Here there is pilot, and it is exclusively transmitted during the pilot frame. Send a pilot frame followed by data frames. Pilot frame goes through this, so that is quasi-periodic, discrete, and then you inside this you could do continuous, and then you do YDDKL. The whole thing is a block diagram that I showed before. Here you simply read off. See here, during the pilot's transmission, YDDKL corresponding to the pilot, I read off. That's it, and that is HFT hat. Simple. Okay, and that I don't do any processing using networking or learning. I give to symbol detection when data comes. It is as simple as that. The channel estimation process, because of the model-free operation, because of the twisted convolution nature, that H effective is there in the read-off region if it is a pure pilot. Okay, and this will give you the estimated data. Now, what I say is this read-off has this issue. Yes. Okay. You have the advantage of simplicity. Simple read-off is order 1, whereas typically quadratic or cubic complexity will be there in Mn frame size in the channel estimation if you do matrix inversions and so on, but read-off is just O1. Maybe at max, if you do some computation, it will be O-Mn, which is order in linear terms. It is natural and effective in acquiring fractional DDs. I think this is a big message that we are trying to convey, because model dependent, what is it? Model free, what is it? People are a little bit mixed up, just like we are. So what is twisted convolution? What is an aliasing? All those things. Now, this model free versus model dependent is simple read off, very complex, less complex. But drawback is it reads only in the fundamental region, right? There are things which are outside depending upon the filter characteristics, which this read off doesn't read. So that is a problem, right? Does not provide estimate for the region outside the region of reading that you read, which you call that as F. So some region you read, outside also there is responses which you don't read, and how to account for it is an issue that you have to deal with. These readout samples are corrupted by aliases and these two. First of all, limited region read off, and even in the limited regions there are aliases and noise, and can you improve that? And that we want to use learning techniques. We go to image processing. You take that read off as an image. There is a mistake here, and this is a mistake. Yesterday night only I saw, I did not have time to fix this. As an image I said, then I said as a DD image should have been, so an is left as such, so mistake. So treat that as an image and then use a conventional neural network to enhance the image, denoise it. That's as simple as that. Okay. Now this picture tells all. So this, okay, before I go there, one picture will be enough. Okay, so, sorry. Okay, so this is enough. So this is the input picture, which is what you read is only the fundamental period, which is this response to a pilot. Outside, I am forcing it to 0 because there is no means of finding out what it is. But the true channel, I think one figure should be there. I think. Yes, why it's jumping twice? I don't know. Fine, leave it. See that slide is moving fast. I don't know, maybe. Fine. So this is a enhanced image. In other words, outside this blue, which is 0, which is at the input, has to have some values, and that I am getting through this network where I have this 2 layers in this example with multiple filters with different kernel sizes and different activation functions, in this case ReLU, to have this image which is enhanced to this image, and this image is an enhanced channel estimate. If I use this, then your mean square error performance of the estimate is going to be much better. In fact, this problem is an extrapolation problem. Okay, in OFDM, you have a time frequency grid. In that grid, occasionally you will have in different places pilot subcarriers. So you estimate channel in only the pilot subcarriers, but in between there are other carriers for which also you have to have the estimate. You will do an interpolation. You will do an interpolation. You have 2 pilots in between on both axes. You can do interpolation, and people have used learning techniques to interpolate, right? So that is an interpolation problem. More importantly, it will be a sparse matrix to a matrix completion problem. The pilots are few in the grid, and that is sparse. And then I have to complete in the entire grid. That is a matrix completion problem from a sparse matrix input. So people have done that. This problem, network we want to use, but I have one region which is read off using measurement, but I need to figure out what happens in the other region, which is an extrapolation problem. Okay, this extrapolation also is done by this network, and this is the enhanced image. If I do that, I'll go and then show these are the parameters on which you can do the thing. You can see one example. This is without this enhanced image. This is with this enhanced image. This is the mean square error normalized of the estimation of that effective channel tap. First of all, this is too good. No, too good means too simple. Too simple here, right? But it is good to work with. But I can do much better if I do this enhancement. My student, once he knew the problem, he just hacked it by just putting some layers and some kernels and some numbers inside that, and then tweaked it, and then he got this performance improvement. BER. So this is perfect CSI. Okay, this thick lines you see, this is perfect CSI. Assuming that it's perfectly known, this is the estimated without the so-called CNN. This is with CNN. You can improve. This improvement in the estimation accuracy gives this performance which is very close to the. So the message is there is simplicity in channel estimation to start with, that can be enhanced using simple CNNs, because this they say it is thin CNN is what they say. My student says at least. So you achieve that. Now these are plots which show the same thing again. It's saying that I can go close to perfect CSI, even higher order form. My training requirements are simple. Many things are positive. So this is another thing which I would say. To avoid this throughput loss, I can multiplex data and pilot using spreading and superimposing on that. In that case, pilot will become an interference to data. Data will become an interference to data. There will be an interference cancellation. But there will be a read off after cross ambiguity, which you do in radar signal processing. You compute a cross ambiguity and do the same thing, and you will again show the images. This is the true channel. You read only in a box. Outside the box, you estimate that you have to get this. This is what you transmit, data and pilot transmitted. This is the channel which I want to read. This is the true value. This is what I observe. This is what I read here after cross ambiguity. I want to get that, and that is what you will get here. You start with this and you will get this. So again, performance can be significantly improved in terms of NMSC performance. One last highlight. This is a last slide, but very, very simple, but very important for ZAC-OTFS. See the x-axis. X-axis is Doppler shift, kilohertz. And see the performance as a function of Doppler shifts or the Doppler spread. Up to 6 kilohertz Doppler, it is flat. It is almost flat. No waveform that we know will have this much of resilience over so much of spread. So this is assumed. OTFS knows that is known that OTFS gives that, but anyway, that is the main thing of both a combination of this without CNN, this is with CNN, perfect CSI close, but more importantly, it is flat across plot band. So this comes to my last slide, which says ZAC-OTFS is a promising waveform for both communication radar sensing. Learning text can be exploited. Lot of scope for research. So it is a field with gold. Anything that you go and touch can be gold because it's new. And with that, I'll stop here. Thank you very much.
Hello.
Thank you, Prof. Chockalingam, for the interesting talk. Are there any questions? We can take the question.
Thank you for the nice talk. I have a couple of questions. One is, you spoke about embedded pilot. Are there better pilot designs than
Yes,
embedded
I think
pilot?
I'll refer to your own work in MCOTFS, where you did superimposed pilots. And superimposed pilots can be done because embedded pilots have the problem of throughput loss because of the guard space that you leave and interference between both. So that is a problem. and the fix can be superimposed pilot. But in MCOTFS that you had done before, as one of the pioneering works of Rohit's group is to put in the earlier version, which is not ZAC OTFS, but something which we call that as multi-carrier. He has put data as well as pilot on the same thing and did interference cancellation to do that. Here also it is possible, but with one advantage. We can spread a point pilot to get that spread pilot on the same data frame to sit on top of it and do a spreading operation, which is using chirp filter, and do a cross ambiguity, which is the despreading operation. So in other words, the pilot and data can be together put in one frame without any throughput loss. They can be separated by a despreading kind of operation, which we call in radar terms cross ambiguity. So the data will be on one period lattice. The self ambiguity of the pilot will be on a different lattice, which is twisted with respect to the base lattice. So they can be distinguished in two different lattices. By signal processing using cross ambiguity, you can separate them, and that is the second half, but I did not talk. Definitely beyond embedded architecture, other things are possible and one can do that.
I was curious about anything other than superimposed, between embedded and superimposed.
Superimposed is better, more signal processing, we can do more papers, students will be more excited. Embedded, industry we are not like because there is loss of throughput. Pilot, which is exclusive, is to start with for students to play with. These are the three we have been playing with, but I do not know. So it is rich. Whatever you can think of more is all open.
One last question. So you spoke about two pulse shapes. One was sync and other one was Gaussian. I saw the plot for root raised cosine and you do not speak about that. Is there any specific reason for that?
Time. Okay, in a short time. The root raised cosine is a pulse shape which is going to have bandwidth expansion, because the factor by which you use the parameter, rise parameter or whatever, that parameter is going to tell the side lobes will go down, but it is at the cost of bandwidth expansion. So it is not a fair comparison. RRC is good, but it reduces the side lobes at the cost of bandwidth expansion by the roll-off parameter. So roll-off parameter 0 is what corresponds to sync. Sync is a special case of RRC. So we do not want to talk anything much about RRC because it is at the cost of 20%, depending upon 0.2 roll-off means 20% extra bandwidth. 0.2 extra T is time expansion of 20%. But whatever we are talking about with filters which do not have any bandwidth expansion. We can take one more question. Saru.
Sir, we are doing the simulation based everything, but what is the status of the hardware implementation of OTFS and OTSM?
Okay, so it's a bigger question which can be treated outside this talk, but it will happen. All I can say is, I tell even in my large MIMO days, if anybody can write a code in MATLAB that is realizable in a chip, don't worry about the power consumption, cost, this and that to start with, because we are academics and we will at best go to a next level of algorithms and maybe in MATLAB. If it is in MATLAB, it is in a chip. So right now it is in MATLAB. So in a chip, it is a matter of time. And yeah, so it's a big question. I think I did not put one slide which shows the cover page of my book, which Saif magazine. I put that multiple occasions. So I thought it will be too much of a repetition, but it is selling well. So I think the interest is more in ZAC OTFS is what we understand. So yeah, sensing.
It might make an appearance in a 6G network for a specific application. So if it is there in the standard, I'm sure like there will be
to get a discussion item into the standard itself is a big challenge. This is what I understand, quote unquote, to get this topic as a discussion item. Forget about being taken into the standard. That is much, much later. There is a issue in just taking that as a discussion item in the standard. After that, there are 10 or 12 sets or more. Even there is an issue at this point, but we will just, yeah. So, thank you.
Thank you, Professor, again for this talk. To thank him for coming here and giving this talk, I would like to invite Professor Reddy to present him with a memento as a vote of